In this video, we're going to use a couple of examples to reveal how to use the rectangular components of the vectors to find the resultant vector, and how to find the magnitude and direction angles of the resultant force. So just a quick reminder, what are rectangular components? When a force is resolved into two components along the x and y axis, then the components are called the rectangular components. So that's why in this video, we're going to actually introduce or reveal examples in 2D. There are only x direction and y direction. To find the resultant vector, we usually take several steps. So in this example, we have three force vectors, F1 to F3. To find the resultant vector or the resultant force, first we need to resolve each force into its component. So here again, we have a 2D, right? We only have x and y axis, so the components will be rectangular components. Each force can be resolved into two components. One component along the x direction, another component along the y direction. The next step is to add all the x component together. Here we have three x components, right? One from each force. And followed by adding all of the y components together. And these two totals are the x and y components of the resultant vector. And from there, the last step is to find the magnitude and angle of the resultant vector. So if you can recall, the unit vector along the x direction is I hat, and it designates the direction of the x axis. And same idea, we have the unit vector along the y-axis is called j hat. So after we resolve a force into rectangular components, we can also use the vector formulation to represent the force. So here are what we can do. Here, the bold red letter means it's a vector. Okay, so on this notation or on this side of PowerPoint, if you see something written in this way, that means it's a vector notation. Okay, so this is resultant vector FR equal to vector F1 plus vector F2 plus vector F3. And each vector is expressed in terms of the two rectangular components, the magnitude along the x direction times the unit vector I hat, plus the magnitude along the y direction times the y unit vector j hat. And same thing for the force vector F2 and the force vector F3. Then we're going to add all the I hat terms together. So this becomes the x component of the resultant force. And the j hat, the sum of the j hat terms, becomes the y component of the resultant force. If we need to find the magnitude, remember the magnitude of a vector is a scalar, it's a number, right? How long this vector is. If we need to find the magnitude of the resultant vector equals to the square root of the sum of the squares of the two components. And you will also be asked to find the angle between the vector, or the angle of or the direction of the vector. So magnitude and direction, right? So if you need to find the direction of the vector, the direction is usually expressed by the angle between the FRX and FR. So this is the theta angle. And theta angle is calculated by the inverse tangent of FRY over FRX, the magnitude of the y component over the magnitude of the x component. But keep in mind, this is the absolute value of the ratio between the two values. Let's see the first example. 3 concurrent forces acting on a tent post. And we're looking for the magnitude and angle of the resultant force. So first, let's review the term concurrent force. Concurrent means those vectors pass through the same point. So that's the concurrent point, and 3 forces all pass through the same point. Okay, so we just said there's 3 steps, right, to find the resultant force or resultant vector in a 2D problem. So here are the plans. First, we're going to resolve the force or forces into their x, y components. And then we're going to add the respective components to get the resultant vector. After we find the resultant vector, we can find the magnitude and the angle for the resultant components, from the resultant components. So let's resolve the forces into their components. First, for F1, clearly it just points to the y direction and positive y direction. Let's specify this is the positive y and that is the positive x. So there's no, for F1, there's no x component, or we can say the x component is 0. It just have the y component, 300 j hat, right? So we can write the F1 in component format immediately. We will have 0 I hat plus 300 j hat. And for F2, there is a 45-degree angle between F2 and the negative x axis. So we need to resolve F2 into its component. So one method to resolve a 2D vector is to use the imaginary walk, or take an imaginary path, right, from the tail to the head of the vector only along x and y. Okay, so use this F2 vector as one example. So this is the tail of vector F2, and this is the head of vector F2. We are going to walk from the tail to the head, but only walk along the x and y direction. Okay, when we talk about direction, doesn't mean it has to be on this line or on that line. So this, any parallel directions are considered as that direction as well. So when it's pointing perpendicular up, this will be all y direction, right? When it's pointing horizontally, it will be all x directions. All right, so now I'm gonna walk along the x direction first, clearly to go from the tail to the head, I have to walk along the negative x direction. So this is the F2x component. And then I need to change direction, right? In order to go to the head, I have to change my direction to walk along the y direction. So this is F2y. And to remind myself, usually I put a negative sign, or I will just leave the positive sign out. So if it's to the negative direction, then you need to remember to put a negative sign before that component, because that indicates this component is pointing to the negative direction. Okay, so after we specify that, remember that's a 90-degree angle, then we can find the magnitude of F2x and F2y. So since these are 45-degree angles, so the magnitude should be the same, right? So just make sure your directions, the positive and negative sign, are correct. All right, so use trigonometry. The x component, negative 450 times cosine 45. And y component is positive 450 times sine 45. Do the calculation, and this is vector f2 in component form. And for f3, we have something called direction triangle or slope triangle, isn't it? So this is called the slope triangle. So it gives us the relation between the components or the magnitudes of the components, to be more specific. Okay, so 3, this is the direction along the x-axis, right? And 4, this is the direction along the y-axis. So this triangle is a similar triangle to the triangle that will make up by this f3 and the x and y components of f3. Okay, if we do the imaginary walk again, we'll have, this is f3x, which is positive, and f3y, that is positive as well. So the bigger triangle made up by this f3x, f3y, and f3 it's similar to this slope triangle, which has the size of 3, 4, 5. Okay, which means the corresponding sizes of those two triangles are proportional. So we can write down f3x over 3 equals to f3y over 4 equals to f3 over 5, which we already know f3 is 600 Newton. And with 600 Newton, we can solve f3x and f3y. Okay, so f3x, after you get familiar with this types of problem, you don't have to write down this ratio because f3x is the corresponding size to number 3, right? So the length, the magnitude of the f3x will be 3 over 5 times 600. And same idea, f3y is the corresponding side to this 4, to the side with the length 4. So the length of f3y will be 4 over 5 because the resultant force, the magnitude is 5, or represented by 5. And this is the f3y component. All right, so let's write down that. This is the f3 vector in component form. So in this single problem, we reviewed if we have a given angle, how do we find the components of the vector? And if we are given a slope triangle, how do we find the components of this vector? So the next step, we will just summing up all the I hat terms and j hat terms. The sum of the I hat will be the fx component of this vector r. We can say this is frx, and the sum of the y or j hat components will be the fry. So this will be our resultant vector in component format and also in the vector format, right, or vector notation. We also need to find the magnitude and the direction angle of this 2D vector. So the magnitude of this fr is just the square root of the sum of the squares based on trigonometry. And the angle, again, this is the angle to represent the direction of a 2D vector, which is the angle between the x-axis and the vector itself. So we use the inverse tangent of FRY over FRX, and it should be the absolute value. If you have a negative component, you're going to use the absolute value of that component, which means the magnitude of that component. The second example are very similar to the first one. We again have three concurrent forces acting on the bracket. The magnitude and angle of the resultant force need to be figured out. And also we need to show the resultant force in a sketch. Similar problems. So just a quick practice for the 3 steps. First step is we're going to resolve the forces into x and y components. And we're going to add the respective components to get the resultant vector. Then find the magnitude and angle from the resultant components. Okay, now to resolve F1. F1 again has this slope triangle. We resolve it using imaginary walk. So this is the F1 of y and F1 of x. F1y clearly is a negative component pointing down, and F1x is a positive. And F1y, the corresponding side to that slope triangle is 3. So you have 3 over 5. 3 over 5 times the magnitude of F1, and it's pointing down, so you have a negative sign before the j hat term. And for F1y, the corresponding slope triangle is 4, so the magnitude will be 4 over 5. And it's pointing to the positive x direction. Therefore, we have a positive I hat term. So this is F1. For F2, same idea, but it's easier because you have a 30-degree angle between F2 and the y, but it's negative y-axis. So again, do the imaginary walk from the tail. So you need to move down along the y direction and then move to the negative x direction as well. Therefore, both x and y component will be negative components, and the magnitude we use trigonometry. So the I hat term is sine 30 times 625, but you have a negative sign also for the j hat term. We have the negative sign in front of it. The magnitude is 625 times cosine 30 degree. Very similar approach for F3. Looks like F3 will have a positive y but negative x. And we do the calculation. So all the vectors are written in component format, I hat and j hat terms. The next step would be summing all the I hat and j hat components respectively to have the I hat for the resultant force and j hat for the resultant force, which representing the FRX and FRY. Looks like both x and y components are pointing to the negative directions of the x and y axis. To find the magnitude and the direction or the angle, we really need to think about the angle especially. So for the magnitude, will be simple, right? The magnitude still be square root of sum of the squares. But for the angle, if we are going to use the given formula, which is theta equals to tangent or inverse tangent, the absolute value of FRY over FRX. Really think, what is this value? So if we do a quick sketch for this force FR, based on FRX, which is negative 162.8, and FRY is also a negative value. So if, again, you can do the imaginary walk from the origin, which will be the tail of the vector, to the head of the vector, we can see this FR actually points to point down, right? Point left and down in this octant. And if you use the formula, this is FRY and this is the FRX. Really the angle we're looking for is this phi angle, indicating here. Okay, and if you do a sketch and specify which angle this value is for, that's okay. Okay, so you're showing on this sketch that the phi angle is the angle here, shown here. But if you're going to use theta angle, okay, theta angle has a specific meaning. Theta angle is the angle between the vector, or between the head of the vector and the positive x direction. Which means you need to do some kind of calculation to solve or to find a relation between the phi and theta. And based on the sketch, let me clear it a little bit. We can find the relation easily, right? This theta angle actually equals to phi plus 180. And you will get the theta angle. Again, theta angle has a specific meaning. It is the angle between the vector, the head of the vector, and the positive x-axis. So, to be safe, do a sketch to figure out where is theta and do your calculation accordingly.